All right, this is section 2.6, proof statements about segments and angles. So, the whole idea of this section is going to be to organize all your reasons and your statements into just a logical fashion to show that this one statement is true. All right, one way to do that is with a thing called a two-column proof. So it's just an organizational way to organize an argument. So, a proof, like I said, is a logical argument that shows a statement is true. One format of a proof, and there's an infinite number of formats, but one is called a two-column proof. And what you're looking at the middle screen down, that is a two-column proof. All right, it has numbered statements. It's got corresponding reasons that say this is why those statements are true. So let's just go through this proof. Now all the statements are written out already. But when you're doing these proofs, what you want to do is look at your picture, go to your given information, and just kind of see, do I think what I'm trying to prove is true? So we've got our points, R, S, T, and U. We are told that RT is congruent to SU. All right, so do I think that RS is equal to TU? Now, we've done something like this in class before, and the answer should be yes. RS is going to be equal to TU. The idea is you are sharing, or these two segments, RT and SU, are sharing this inner segment, ST. So if you take away that inner segment, ST, you have RS and TU left. Equal things, take away the same thing, you're left with equal things. But let's talk about the organization here. So, when you have a two-column proof, you got this left column that are statements, you got a right column that are the reasons why the statements are true. And so the reasons, they're definitions, they're postulates, they're theorems, things that are known to be true. In a two-column proof, you always start with the given information. You were told RT equals SU. There it is. The reason it's true, because it is given to you. All right. So now, you start looking at your picture, looking at your given information. You're trying to make a couple statements to get to an argument that says whatever it is you're trying to prove is correct. So looking at this picture, we know that RT equals RS plus ST. That's just a segment addition postulate. You're adding two smaller segments that are on the same line and getting a bigger segment. Remember, postulates are things that are accepted to be true. So, segment addition postulate is why this statement, number 2, is true. And we're doing the same thing for statement 3. Segment SU is segment ST plus TU. So, the reason is true. Segment addition postulate. All right. Once you get a couple of statements from information in the picture, information from what you're given, then you start putting some things together. Well, you look at statement 1. It says RT equals SU. In statement 2, we said that RT equals this. So what we're going to do is basically like a substitution. We're going to take out this RT and put in RS plus ST. Statement 3 says SU equals this thing. So we're going to take SU out and replace it with what we just said it was equal to. And there's statement 4. RS plus ST equals ST plus SU, or ST plus TU. We just did substitution. Terrible spelling. Substitution. All right, that's why statement 4 is true. From what we had above, we just did a little substitution, we got a true statement. And so just like I did with the eraser here, you look at statement 4, if you subtract ST from both sides, you've got RS equals TU. So the reason statement 5 is true was the subtraction property, or is the subtraction property. Okay, that's a two-column proof. Statements are organized in a logical way. We're giving the reasons on the right side of why those statements are true. So like I said earlier, the reasons used in a proof, their properties, their definitions, their postulates, they're things that we know are true. New term, theorems. Theorems are statements that can be proven. Or postulate was just something we kind of accepted as true. We don't need to prove it. It's a common sense kind of thing. A theorem, you can prove it. So you can just go through an argument that says, here's why it is true. Now, you got these two theorems here. They are basically the same thing. It says congruence of segments. The other theorem is congruence of angles. Okay, so we got two different contexts. One segments, one angles. But the properties are the same. Okay, the reflexive property. We use this every so often. It shows up quite a bit in the homework. Just something is equal to itself. Okay, so on the top we're just saying two segments are congruent to each other or to itself. On the bottom we're just saying angles are congruent to themselves. The symmetric property, we don't see it very often, but it's there. Basically you're just switching left and right side of things that are congruent to each other. So on the top it's segments, on the bottom angle A congruent to angle B. You could rewrite it as angle B congruent to angle A. You're just changing the order of your equal sign. We don't use it very often, but it's there. Transitive property. We use this all the time. Okay, again, same thing, top and bottom. Transitive property, you have AB congruent to CD. You then know CD is congruent to EF. So, CD is the same thing. So we can just make this jump. AB is congruent to CD, which is then equal to EF. So the conclusion is AB is equal to EF. It's the same thing down here with angles. It's the transitive property. It's the same pattern of things, whether you're talking about segments or you're talking about angles. All right. So this example just goes with that last slide. Just name the property that's illustrated with the statement. So in this one, angle RST congruent to angle MNP. Now we got angle MNP congruent to RST. We just switched the order. Symmetric property. And the second statement, AB congruent to FG. FG is congruent to segment MN. Well, FG is the same thing in both of them. That means these two must be congruent to each other, which is what the statement says. That is your transitive property. And that's it. Okay, so let's go through doing a whole two-column proof. Always start with the given information. It's the only thing you can start with. So it says B is the midpoint of segment AC. There's segment AC. B is the midpoint. It also says C is the midpoint of BD. Well, that means this segment just continues. Didn't draw it very well. There's point D. So C is the midpoint of BD. So this is all just one segment. Just poorly drawn. The question is, can you prove that AB is congruent to CD? Well, so when you're doing these proofs on your own, start with the given information, look at your picture, and just go through the argument in your mind. Do you think what you're trying to prove is true? All right? B is the midpoint of AC. If something's a midpoint, it's cutting it in half. So we know AB and BC are the same thing. C is also the midpoint of BD. That means BC and CD are the same. And so you can see these three smaller segments, they're all the same. Okay, you kind of got a transitive property going on here. So looking at the picture, AB and CD are the same thing. So we think it's true. So here's how we organize the proof. Your statement one is always the given information. So you're just rewriting it. B is the midpoint of AC. C is midpoint of BD. Okay, and the reason that stuff is true is because it was given to us. So now, just like we did when we were just looking at the picture and putting in the information, we use the definition of a midpoint. If B is a midpoint of segment AC, that tells us that AB will be congruent to BC. And I'm going to change this problem here, just add a little bit of detail to it. Let's make this segments congruent. So AB is congruent to BC. Why is that true? Well, we were told that B was a midpoint. So from the definition of a midpoint, we know that AB is congruent to BC. Now we can do the same thing with our other piece of given information. C was the midpoint of BD. Definition of midpoint says that BC is congruent to CD. Definition of midpoint was our reason why that statement is true. All right, so now we're trying to get to segment AB congruent to segment CD. If you look at statements 2 and 3, you kind of got that transitive property set up here. AB is congruent to BC. BC is congruent to CD. So according to the transitive property, AB is going to be congruent to CD. And that's our statement we were trying to prove. So this proof is done once we give this last reason, transitive property. That's the idea of a two-column proof. There's a logical progression of statements from the given information to what you're trying to prove. It's nice and ordered in number. You're given your reasons why the statements are true. All right. For this example, it's not a two-column proof, but we're using the same logic. You start with a given information. We're trying to solve for x. So you start with the given information, and you go to the picture. You're given angle ABD, this one, is congruent to angle DBE, this one. You were also told angle EBC, which is this one in green, is congruent to angle DBE, that same one. Well, transitive property says if this one and this one are equal, and this one in red is equal to that one, then they got to be equal to each other. The outer ones are equal to each other. And so that's how we're going to solve it. 14x minus 10 equals 11x plus 5, just with the transitive property. Angle DBE is the same angle. It's congruent to these two angles, so then these two must be congruent. And so we just set them equal to each other. And now we solve for x. So I'm going to subtract the 11x from both sides. We can do that, or this new statement is true because we subtracted the same thing from both sides, subtraction property of equality. Then I'm going to get this statement. I just added 10 to both sides. We can do that because that's the addition property of equality. And then we get to our answer statement, which is this. All we did was divide by 3 on both sides. That's the division property of equality. Okay, so it's a proof. We're used to this kind of proof because it's just algebra, but it's still a format of a proof. Okay, it's same logic. That's it. Bye.